This new unit is going to be on probability. So we're going to be talking about lots of different types of probability. Today, we started class by looking at what happens when we toss pennies or flip pennies, and what happens when we roll a die. So what I had students do in class was I gave some of them pennies and I gave some of them dice, and they had to either roll the dice or flip the penny 10 times and then record how many heads or tails they got if it was pennies, and how many of each number they got if it was dice. So you see here the results. If you look at pennies, the first person had 4 heads and 6 tails, the second person had 5 of each, third person had 7 heads and 3 tails, and so on. You can see with dice, the first person had 0 ones, 4 twos, 1 3, 3 fours, 2 fives, and 0 sixes. And then you can keep going on down. There were 9 people with dice and 8 people with pennies. Now, what I was trying to illustrate here is theoretically, you've just got 2 possibilities with a penny, heads or tails. Theoretically, you've got a 50-50 shot at getting heads or tails. So what you would expect would be results like these, where you get a 5 and a 5, because you'd expect that there's 50-50 shot. You don't typically think of you getting like a 7 and a 3. But it does happen. And the reason for that is a difference between what's called experimental probability and theoretical probability. Okay, experimental probability is what actually happens. This is probability taken from the actual experiment. So for example, for this person, the probability of getting heads was 4 out of 10, and the probability of tails was 6 out of 10. For this person, it was 5 out of 10 for heads and 5 out of 10 for tails. Now, you contrast that with theoretical probability, and that's what we expect to happen on average over a period of time. So, we would expect for pennies that we would get an equal number of heads and tails, since the probability of getting either heads or tails is equal, 50% or 1/2. So this person, the theoretical, matched perfectly the experimental, and that certainly can happen, but as you can tell, it doesn't always happen. So experimental probability is what actually happens and the probability taken from that. Theoretical is what we would expect to happen in a perfect world. Another word I wanted to go ahead and introduce you to is the word fair. A fair game or a fair scenario is one where each outcome has an equal probability of occurring. So flipping a coin is an example, rolling a die is an example, randomly drawing one card from a deck is an example, things like that. So fair implies that each outcome has an equal probability of occurring. Alright, so today what we're going to be talking about is called the Binomial Theorem. Okay, so I'm going to try to illustrate that here for you. This is the Binomial Theorem. So first of all, a plus b raised to the 0 is 1. Anything raised to the 0 power is 1. A plus b to the first, I'm right here, is just 1a plus 1b. You don't have to draw those ones. You'll see in a few minutes why I bothered even drawing those. But a plus b to the first is just a plus b. That's the point. Now a plus b squared requires you FOIL it. So you have to do a plus b times a plus b. So you end up with a squared plus 2ab plus b squared. This is the result of the first terms being multiplied, a times a. This is the two middles, the outer and the inner. So a times b plus a times b gives you that. And then the last terms gives you b squared. Alright, now you can continue that process on down here, but I just wrote these so you can see how they work. Now what you need to do is try to notice the pattern we see here. Okay, so first I would recommend you look at the exponents. So let's just look at one of the bigger ones because it's a little easier to see. If you look at the exponent of a, for example, a is always going to represent our first term. So our first term here is a. It goes a to the fourth, a to the third, a squared, a to the first, and then there's no a, which means a to the 0 power. So we always start with whatever number we have right here. In this case, to 4. So a to the fourth, and then we go down one each time. 4, 3, 2, 1, 0. B, our second term, does the opposite. It starts at 0. That's why there's not one that shows up here. B to the 0 is just 1. Then B to the first, B to the second, B to the third, B to the fourth. Another thing you may notice is that if you add the exponents together in each individual term, they'll always add up to this number right here. Here it's just 4. Here it's 3 plus an understood 1, that's 4. 2 plus 2 is 4. An understood 1 plus 3 is 4, and then 4. If you notice, it's the same thing down here in the one that goes to the fifth. 5, 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4, and just 5 by itself. The last thing I would encourage you to notice about exponents, or not exponents, excuse me, is that there's always one more term than our exponent. And we're going to call this exponent n most of the time. So in this case, n equals 0, and we have one term. In this case, n equals 1, and we have two terms. N equals 2, and we have three terms. N equals 3, and we have four terms. So your number of terms is always one greater than your exponent. So I wrote these observations out. Sorry, it's a little messy. But a plus b raised to the n power. So just in general, your a, your first term, starts with an exponent of n and goes down by 1 each time. Your b starts with an exponent of 0 and goes up by 1 each time. And the total number of terms is going to be n plus 1. So again, if you're doing a plus b to the 7th, you'll have 8 terms. One more term than the size of your exponent. Alright, so there's also a pattern we see with the exponents. I'm actually going to come back to that slide in a second. So I want you to look closely at the exponents here. We had a 1, then we had a 1, 1. Then we had a 1, then a 2, 1. 1, 2, 1. Then 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. Now, I don't know if you see the pattern yet, but I almost guarantee you've seen this before. Let me just write just the numbers up here. First line had 1, second line had 1, 1, third line had 1, 2, 1, then 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. This is called Pascal's triangle. Sorry, it changed on me there. Hold on. There we go. Pascal's triangle. And it keeps on going forever and ever. You can take it down as many steps as you need to. But the ones just continue on the edge, but then how you get the numbers in the middle is you add them. So let me use my mouse here. 1 plus 1 gives you 2. So that's how I get that number. 1 plus 2 gives me 3. 2 plus 1 gives me 3. 1 plus 3 gives me 4. 3 plus 3 gives me 6. 3 plus 1 gives me 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And again, the ones are always just the same all the way down the line. This is called, again, Pascal's triangle, and this is the pattern that your coefficients will follow. So now let's look at this, the definition of a binomial coefficient, because this is the binomial theorem that we're looking at. Okay, it's written this way, with the parentheses and then n on top and r on the bottom, and it's read n above r. So this means n above r. And this is the formula that you can use to find it. You can use factorials. The good news is your calculator actually can do this for you without you even having to do the factorials. It's the same thing as the NCR, which we're going to talk more about later in the unit. So tell you what, I'm going to go ahead and stop here. The video's getting kind of long, so there will be a part 2. Just make sure to check it out.